I'm Guido Tuck from Monash University in Australia, and today I'm interviewing my esteemed colleague, Peter Stuckey. So, we're just going to talk a bit about how you got into computer science, into constraint programming, what you see as the future of the field, all those sorts of topics.
Yeah.
So maybe we start right at the beginning. So, where are you from? What brought you to university? But let's start right at the beginning.
So I guess I was born in country Victoria. I was actually born in Melbourne, but I lived in country Victoria because my dad was a forester, so we lived out in the wilds. And then we came to Melbourne when I was going to start secondary school. So I'm basically an Australian, born and bred. So that's where I come from. Is that an answer?
Yeah, absolutely. And so, were you already interested in science, those sorts of topics in school?
I guess I was good at maths and those kind of things. And the first computer I saw was the school bought a PDP-11.
Oh, wow.
And I played Colossal Cave, the original adventure, and I was like, whoa! I mean, typing in instructions and the computer doing what you're told. I mean, obviously it was a very limited language, but it was just eye-opening. I remember that very distinctly.
So you were just allowed to use the computer in your free time?
Oh, no. So they had, when they brought it in, they set it up and various people could try it out, and I tried it out, and the Colossal Cave was like, wow, this is something totally different. And so then, from then we got computers at home because the personal computers were just starting at that time, and Dad was interested, which was lucky. So, we had personal computers, and I was doing basic programming and these kind of things when I was in school. And then I came to Monash University planning to do a PhD in physics.
Right.
Because I thought that was the best subject that I enjoyed the most at school.
Do you want to give us a rough decade?
Oh, okay. I arrived here in 1980. That was when I started my undergraduate degree. But first year physics was terrible. It was a repeat of the last year of school's physics, or it was quantum mechanics, which made no sense whatsoever. So I sort of got rid of the physics and started doing more maths and computer science. And I think I only decided to do computer science near the end when I was looking for a summer project, and there was this guy, Jackson Jaffa, who had a title of a project which I didn't understand at all. It was infinite tree unification. And I was going, what on earth does that mean? And so I went and talked to him about it. It was fascinating. Yeah. And indeed, that summer I worked on infinite tree unification, which is, of course, a constraint-solving algorithm. Yeah. So that was my start with constraints, I guess.
And that was your first time you did anything with kind of formal logic and logic program, anything related to this?
Anything to do with, logic, actually. I think I had to wait till fourth year studies to do logic as a subject. Yeah. So, of course, we'd done grammars and all that kind of classic computer science, but no logic or any constraints until that point. And then, because of that, I went on to do a PhD with Jackson, and that was all about kind of infinite tree logic programming and the beginnings of constraint logic programming, at least. Yeah.
How did you find a PhD back then? Is it very different to what
completely different. I mean, I'm not allowed to tell my students how my PhD was because it was a theoretical computer science PhD, so I didn't spend a lot of time here. And indeed, I wouldn't even have been involved in CLPR, which was the first constraint programming language that we sort of built here at Monash, and it was sort of one of the first three in the world. I wouldn't have even been involved except that Jackson was convinced that we should use this Shostak's algorithm for solving arithmetic constraints, and it was ridiculously complicated. And I was going, but hang on, I learnt about the simplex algorithm. So I implemented the solver for CLPR because I was just so confronted by this crazy algorithmic stuff that they were trying to use, and that turned out to be a good idea, it turns out.
So did that become part of your PhD then?
So not really. CLPR was kind of on the side. My PhD was much more about the theory of constraint logic programming, at least the infinite tree version, and so I basically was sort of building towards the foundations, and then Jackson and Jean-Louis Lassalle sort of defined the constraint logic programming framework, which is one of the kind of underpinnings of the CP community, I guess, at least from one side.
So what was it that actually got you interested in constraints and logic and?
Well, I think
algorithms?
I mean, I loved algorithms, and when I did this summer project on inventory unification, there I was doing a constraint solving algorithm, and then I realised that I'd done some linear programming, Gauss-Jordan elimination. You sort of now look back and you go, oh, these things are actually constraint solving algorithms.
Yeah.
And so, yeah, that was the interesting thing. And then I guess from there, since I was here and we were building CLPR, it was very natural. That was exciting, a lot of interesting things happening. So that's where I went from then on. But it was definitely logic programming first, more than constraint programming.
Yeah.
Yeah.
So was that also your first contact with the wider logic programming community?
Yeah, so ICLP was here in 1987. So I was finishing up my PhD, but then the whole community came here, and it was a conference. It was fantastic, of course, where you sort of get to see the real world. I was meant to go to ICLP in '86, but I got sick, so I couldn't go. I had a paper there, but I couldn't attend. So that was my first conference, and it was here locally and very exciting.
So you finished your PhD around 87, 88?
Yep,
or something like
88,
that.
yeah.
And then, I mean, it sounds like you've always been here, but you...
No. So straight after that, I went to IBM. So basically, IBM sort of bought Jean-Louis Essay and Joxon, the whole group, and we all went over there in various bits and pieces. And that was very eye-opening.
So that was IBM in...
IBM TJ Watson lab, yeah. So it was, very different. You sort of felt like you were much more in the stream of research because, amazing talkers would come in every week and you'd have great things. But it was actually the least productive time in my career. So there was a lot of other stuff, even though you think, in a research lab, you just get to do research. It just felt like, it's also that point where you finish your PhD and now you have to become your own independent researcher, and that's always a challenge in some respects. Yeah.
But you obviously managed to do that, and then you came back to Australia.
Yeah, so I came back. I was actually at Monash for like 3 months, and then I got a position at Melbourne Uni. And so, I was at Melbourne Uni for 28 years until I moved to Monash in 2018.
Yeah. So at Melbourne Uni, that's really the core of your academic career.
Yes. Exactly. Now I'm an old fogey and I don't do much.
I think some of your hobbies are somewhat related to your job. So tell us about that. What do you do in your free time? Do you have free time?
Well, I'm pretty good at making free time. I'm not a workaholic like some of the people in my group. So obviously I've been interested in computer games right from the beginning.
Yeah.
So as I said, Colossal Cave, wow. And then, writing basic computer games myself on our own PCs at home. And then...
What was your first computer at home?
It was called a CompuColor. I think it had 16 kilobytes of memory. Mm-hmm. But it had a floppy disk, so it was actually quite advanced because it wasn't tapes, which is what, the Commodore 64, things like that were being at the time. And then we had an Amiga. We went through quite a long chain of computers at home. So, computer games I still enjoy. It's a lot of fun. I'm a bit jealous. My sister did a degree in fine arts and then a degree in architecture, but now she's a researcher in computer gaming. And so she gets given free computer game consoles by the manufacturers and things like this. So I sort of wonder when I went wrong, but... I do like the part of computer science that I do. And I sort of think juggling is another thing that I was interested in. In fact, at the end of my PhD, I was kind of I was actually making a lot more money out of juggling than I was out of my PhD stipend. But I think I realized that the 50-year-old street performers that I was, performing with were still getting paid the same as my 24-year-old. So it probably wasn't a long-term career of benefit.
I think you also play a lot of board games, is that right?
Oh, true. I play board games, that's true. So I have a long history in role-playing games. I've Dungeons and Dragons and these things. And it's been very interesting seeing, because we were the nerds at school when Dungeons and Dragons first came out, going off and hiding in the corner and having our imaginary adventures together. And over my lifetime, that's suddenly now we're mainstream. This is now Big Bang Theory, Stranger Things. role-playing games are, and of course role-playing games on computers are like one of the key kinds of games that you can play, and it's been funny to watch that transition over my lifetime from we're this tiny little outcast group of people doing this weird stuff to now a very mainstream activity. I do play board games as well. Love them. Well, they're combinatorial, right? A lot of them are with limited information and a finite set of moves, decide what to do next. So things like that, and puzzles like Sudoku, which, I mean, Sudoku is like the perfect thing to explain CP to someone.
A great gift to our community.
Absolutely,
right? So,
absolutely. Before Sudoku, it was very hard to explain CP. With Sudoku now, it's very easy, because if you do Sudoku, you are doing propagation.
Yeah. Let's talk a bit about your time after your PhD and the most important contributions to the community, maybe from your point of view.
Yeah, so I'll sort of maybe one of the great times for CP in Australia, for sure, was that there was this National ICT Research Centre called NICTA that I was a part of. And yeah, at some stage, the optimization group there was amazing. I mean, very world-leading in many respects. We had Pascal van Hendrik running the group. We had Toby Walsh in the group, me in the group. And yeah, so we got to do what we call the G12 project, which I was running for a long time. This was the Group 12, so zinc, cadmium and mercury was a sort of approach to constraint programming where we talk about modelling in zinc, transformation in cadmium, and then solving it in mercury. In the end, although it was successful, the main thing that really came out of that was mini-zinc, which is in 2016 at the conference, everyone was complaining that there was no standard for constraint programming.
I think that was 2006.
Oh, 2006. Okay, yes, you're right. Yes, you're right. I'm only a decade off. Now I'm too old. That there was no standard. And so, yeah, we sort of come back and said, well, we had zinc, but zinc was a very complicated thing. Let's cut it down to try and get a minimal thing that we can all agree on. And, yeah, eventually mini-zinc arose from that.
Yeah, that was a great time. I had the opportunity to visit you for a few weeks in 2007. Very lucky to be there
exactly.
At the start of mini-zinc.
Exactly.
Yes.
Because I'll say this, that Guido is the chief person in charge of mini-zinc now, so it's good that his name's on the mini-zinc paper.
Yeah, no, I'm very grateful for that.
Well, we're very grateful to have you here.
Well, NICTA was amazing. I mean, that time was really where it seemed there was almost infinite money available. Not quite. I mean, it must have been different from your point of view.
But no, we had a big group and we could work on. So we could do bold things. So G12 was a multi-year. Like, I don't know, probably went for 7 years. And overall, in the whole optimization team, there was probably 30 people. So we were including all the PhDs and things like this. But yeah, it was a lot of fun, and I think we did some really interesting things during that time.
So G12 was mainly about modeling and transforming problems, but you've also made some significant contributions to solving. So maybe let's talk about
those. Lazy clause generation arose during that period too, and that was kind of a reaction. I remember. So one good thing is in the optimization group we had people from theorem proving, so they made us aware. So Peter Baumgartner indeed made me aware of this whole SAT modular theories approach to solving, and that sort of place where you used a SAT solver to do all the inference, but you had, the complicated reasoning sort of on the outside. And that's very similar to what happens in a propagation solver. You have propagators doing all the complicated reasoning, and then they're connecting through domains, essentially, in the search engine. And so, we were made aware of that, and then I remember seeing a paper by someone, I can't remember who now, where they were building a SAT model for a scheduling problem, and they generated millions and millions of constraints. So they could only sort of tackle the smallish scheduling problems. And it just seemed so wasteful, right? That they were generating this huge definition of all the possible things that this constraint could do. And that's basically where the idea for lazy clause generation came from, saying, well, we only have to basically when a propagator decides, here's some new information I can give you, well, we can just add that as a clause into the build up the SAT model of our problem lazily. And turned out that was, quite a good idea. Even though I think it was sort of, we'd written a few papers about it, we showed some results, but then when we did the cumulative constraint decomposition, we didn't build a propagator or anything like this, but just looked at some scheduling problems with the cumulative constraint, and it was worlds ahead of the existing approaches. Yeah.
And of course, nowadays, all of the the top CP solvers all use exactly this method.
Yeah.
Right? So Google's CP solver uses this method. We're still developing the solver here that is based on the method. I think Choco integrates something similar.
Choco
now.
has a different kind of learning, but they're also moved to lazy clause generation style as well. So yes, it feels like it's the right technology, let's say, for a lot of combinatorial problems.
Maybe we could talk about some of the awards that you've won for all of this, because for Chuffed, so for the solver that came out of the LCG Lazy Clause Generation project, you won the Eureka Prize, right?
Yeah, well, for the definition of lazy clause generation, right. Really, the Eureka Prize for innovation in computer science, which is run here by the Australian Museum. So, at least in Australia, it's a well-known prize. And I also surprisingly got the Woodward Medal at the University of Melbourne, which is for the best publication in science. And usually that goes to medical people, right? Because they got their Nature and Science papers. But somehow I snuck that in too. Yeah.
I don't have a list of all your best paper awards, all those. There are a couple.
Yeah, there's quite a few.
And of course you were also awarded the ACP
Research
Excellence Award. That's right.
Which is why this interview is going on.
Which is why we are doing this interview, exactly. So we should definitely mention that as part of the interview. So all of this was like the G12 project, obviously finished up with the end of NICTA. NICTA was basically rolled into a larger IT research center here in Australia, but the optimization group basically disbanded.
Yeah.
Although a lot of people are still in Australia, right? A lot of them are still here. A lot of them are still active in the constraint programming optimization community, of course. The main development on LCG also, I would say, finished around that time, right? So there were, of course, as always, incremental advances after that.
Yeah.
So what have you been doing in the last 10 years?
What have I been doing in the last 10 years? So I'm still I'm still interested in lazy clause generation, but I've suffered from not having the right personnel or to be able to pursue it the way I want to. But I mean, modeling, so MiniZinc has been, been expanding. I think I'm very proud of that approach, and actually I think that's something where I think CP has or will win. We win the modeling game. It's just a better way of having to do things. If you compare like doing traveling salesman by having to write down the MTZ decomposition yourself in linear programming, rather than CP, you just write cycle and that's it. And actually you don't even know how it works. It doesn't matter. And it'll work differently for different underlying solvers. So I feel like I'm very confident that the CP modeling approach will be the winner. And actually I suspect already most users of MiniZinc are using it to run Gurobi or Cplex, but they want the ability to like model with variable indexes. Just the element constraint, which we've had in CP right from the beginning, is so powerful, and it makes you able to write much more compact models than if you have to think about zeroing variables with 5 different indexes, which is the kind of approach if you're doing MIP instead. Yeah.
And of course, in language like MiniZinc, it's almost invisible, right? I mean, you just write down an expression and you don't even think about that this is maybe a complex thing that the solver might not.
Yeah, and that's interesting. I mean, that's one of the challenges for modeling in general, but also for CP modeling is if you only have this high-level view of what this actually does, do you understand if it's going to be efficient or not? But I still think that we can learn about that and which solving technology, and maybe eventually we get to the point where we don't have to. And a lot of it, we're just doing the right translation or some systems picking the right model, the right underlying solver or the right translation to the solver, and yeah, so that removes a huge burden because modeling discrete optimization problems from scratch is not an easy task.
Apart from working on minisync and solvers, you actually gave a really nice talk to our graduate research students here a while ago about curiosity-driven research, and I just wanted to maybe use that as a segue into some
of the other stuff. Yeah, so exactly. I mean, that has been one of the interesting parts of what I've been doing recently is working on election auditing, and you're going like, why on earth, how does that relate to optimization? Well, it turns out in Australia, all of our elections use ranked choice voting, where you don't just say, I want this candidate, but you rank the candidates in order. You can give a partial ranking. And so it was not thought possible, so this instant runoff voting election that we use, where you basically give all the candidates their first preference votes, and then you take the candidate with the least votes and you eliminate them. And then you take all their ballots and you give them to the next person on the list. And you keep doing that until one person's got more than 50% of the votes. So this style of election, it was not clear whether we could actually write statistical audits for it because it's combinatorial, right? You've got to consider all the possible election orders. That's where the combinatorics comes in.
What are you trying to achieve with an audit?
So with an audit, you're trying to present evidence or be statistically sure that the result that you published at the end, that this person won, is the correct result. Now, you don't want to do that. In the end, you might have to do it by looking at all the papers again, but there are statistical methods where we want to look as few papers as possible in order to guarantee that. And so it turns out it's a very nice combination of statistics and combinatorics. And so that's where I became interested in it. And yeah, so we've done some work in that field, and that's really exciting because now that's actually being used to audit real elections. So that's really cool.
That's mostly in the United States?
Yes. Yeah. The electoral system in the US is so bad for many, many reasons that actually they're leading the world in auditing because you really want to audit some of the elections there where it's hard to trust the Electoral Commission because it's run by the governor who's elected by that Electoral Commission.
Right. So let's talk a bit about the future of CP. Yeah. Right. So you've been a part of the community for a long time,
yes.
Basically since the very start of the CP conference series, for example.
Yep.
Maybe can you remember the first CP conference that you went to? Was it the first CP?
Yeah, I went to CP. Well, I went to PPCP before that, which was in Orcas Island, which was a lot of fun. I had to get there by seaplane, and it's a big adventure. But yeah, I went to the first CP conference in Marseille, and that was great. Obviously, I met a whole lot of people that I've worked with for many years after that.
Yeah, I remember that when CP was in Sydney, and you were the program chair.
Yep.
I thought, okay, maybe that's an opportunity for Peter to not be jet lagged at a CP conference, but no.
Yes, that was my plan. My plan was finally I would attend CP and not be jet lagged, but it turned out I was on sabbatical in Spain at that time, so I had to fly back. And in fact, I was more jet lagged because, at least for me, going east is much worse than going west. So I was more jet lagged for that CP than most. And just to repeat that, CP ARR is in Melbourne next year, and I will be in Europe, and so I'll also be flying back for that. So it's clear that I should never be not jet-lagged at a CP conference.
I guess that's why we had to have a massive group assembled here with Nikta, because we are very far away from everybody else, so you have to bring people here.
Yeah, it's true. Although, I mean, until the pandemic, I think we had a lot of visitors, and I guess we're beginning to get back to getting a good flow of visitors through here.
Yeah. All right, so the future of CP. We talked a lot about your contributions in particular. So you've seen the entire history of the field develop. Where do you see it going?
So I think, as I said, I think we will win the modelling game just because it's easier to use CP modelling than other ones. And I think that, eventually that means that CP modelling should be the way we're teaching OR to OR classes. Now that's a long-term prospect because we just don't have that many people who know CP, but I suspect we will win that race because it's just easier, and making optimization more accessible is just a fantastic thing anyway. I think another great space for CP is in certified optimization. I mean, we can use the same tricks as the SAT people to certify our optimality proofs. They're slightly different, and there's lots of interesting work going on that now, so I think that's really exciting work. But then, because we've got the modelling packed as well, if we can certify the model translation from your high-level model down to the solver, then I think we've really grabbed the whole problem and be able to certify from high-level model down to actual runtime that everything is trustworthy. And I think we're in the best place to do that, because MIP always going to have problems with floating point numbers, so at the bottom level it's hard to certify them. And SAT, you can certify that this proof of uncertifiability is correct, but who's certifying that the 2 million clauses you generated to define the model actually define the problem you care about?
Yeah. And as you said, right, that results in something that is more trustworthy. That
yeah. So you want your trust base to be smaller, but you still be very confident that at least the model. This is the correct answer for the model. Of course, the model can still be wrong.
Yeah.
We always have that problem.
So where do you see the connection to approaches that are based on deep learning, reinforcement learning, those sorts of techniques? Because obviously there's a lot of interest in those areas at the moment.
Yes, yes, exactly. And I'm very interested in that too. I mean, I work in formal explainability, so trying to reason about some of these systems and actually prove properties about their behaviour, and it turns out is almost impossible. And in fact, I'll make a bold claim that you'll never be able to prove anything about a large language model, anything that makes something sensible, as in we can trust the results or something like this. First of all, it's very hard to state it, but even then I don't think it's provable because the systems are just too big. There's no formal reasoning method we can apply that'll ever get there. And so this is interesting. I see this kind of castle of sand a bit building, where turns out, I didn't know it, but I was an AI professor all the time. So optimization and discrete optimization certainly is part of AI, but the AI that's hot at the moment is a completely different thing. Yeah. And it doesn't do formal reasoning well. And in fact, it makes lots of errors when you need formal reasoning. So, I mean, this is something I'm interested in. I'm interested in neurosymbolic systems where we try to combine the two. But my feeling is that we're going to have a big crash, just like we did for the last AI boom. And when we start finding out, some disastrous results from trusting these AI systems. But yeah, certainly at the moment, AI, large language models, diffusion models, whatever, these are the things that are hot and interesting and a lot of money. So that's another thing that's changed over my career, is that academia is now way closer to industry in the sense that they can see, things like AI, it's really being driven by industry, not by academia, because there's so much potential money in it.
Yeah. And we're at the point where universities can't afford to actually develop these models anymore.
Right, exactly. I mean, you need so much data to do it well. So only the people who've grabbed all the data can do it.
The other big topic, and this is coming back to your first year university days. You said that you didn't understand quantum physics at the time.
Yeah.
Obviously, the other big topic at the moment is quantum computing, and one of the potential application areas is optimization. So, how do you see the connection there?
Yeah, so that's interesting, and I've been to quite a few talks on this space, and I basically would say I completely disbelieve we're ever going to get any advantage in the optimization space from quantum computing. In fact, there's proofs that it can't solve NP-hard problems in polynomial time, right? But it can massively reduce the time if it would work. But I guess talking to the experts, even then, it feels to me like there'll be some definite uses for quantum computing. We know that we're moving to this post-quantum crypto world, because we can factor integers, or we should be able to factor integers very quickly. So some of the basis of current cryptography just doesn't work. But I'm completely unconvinced that it's going to help for optimization in general. And I think that the trouble is you need to map. Our problems are quite big compared to the number of qubits that we have now. And the bigger the problem gets, the more the coherence. I can't remember the technical term, problems that you have anyway. And so it's not clear to me. I mean, that's the interesting thing that people don't realise about combinatorics is the numbers grow really, really quickly.
Yes.
And, if you've got the slightest error, then, it can be, all meaning can disappear very quickly because the numbers grow so quickly.
Yeah. In addition to your contributions to core research, like core algorithmic research, modeling language, and so on, I'd like to talk a little bit about your industry projects, your more applied research, and maybe you can give a few examples of industry partners you've worked with and what your experience was with that.
Yeah, so I think I'm terrible at working with industry. I'll start by saying that. I have worked with industry. We did a lot of work with the mining industry in Australia because that's a big area, and during the boom times they have lots of money, and then suddenly it's not boom times and then zero money. And that was really eye-opening because I saw how inside even a single company, the divisions were fighting against each other. So even though this was a company that owned all the infrastructure and the mines and the port and everything, we could come up with a sort of global way of, solving the kind of mining problem to get a uniform product to port, but that couldn't be implemented, even though this was a single company, right? So yeah, it's been very eye-opening for that perspective. I do agree that working with industry is great in the sense that the real-world problems are much hornier, much more intricate. There's all kinds of weird things that you don't think of when you come at it from an academic perspective. So I do appreciate working with industry in that sense, but yeah, I'm also terrible in the sense that I really want to be given the problem and find a solution, and and I'm happy, and write an academic paper. I'm not very interested in reports or the timelines for industry, which tend to be much faster than I'm kind of comfortable with. So, yeah, I think in optimization you should definitely be talking to industry, and sometimes we've had quite good successes with industry, but it's also kind of anti-academic. They really have different measures of what success is than academia.
So we have a pretty big group here doing optimization, which you lead here at Monash. And do you think that's a good model to have a diverse group of people doing both more fundamental research and then the more applied side?
Yeah,
I think seems to work well.
I think when I look at so what happened to the optimization group at NICTA, what the remnants of it that were left in the research organisation. So that research organisation doesn't do fundamental research. And I think what happens is after 10 years of sort of doing contract research, you become irrelevant. In fact, industry is ahead of you and you've got nothing to offer. So you definitely, I feel like optimization is a really interesting space because we are so directly usable by industry. But it's still very important to be working in the fundamentals because industry doesn't have the timeline to do those kind of things. Although it's true that we have had some long industry engagements with our group, and that's been great because we have developed some really interesting and novel solutions to complex industry problems, and you don't get to do that unless you get 5 years to sort of learn a lot of stuff and go through many iterations.
Right, we're coming towards the end of the interview, but I wanted to ask you about your recommendations for people who are just starting off in the field. So what should a young researcher in logic, in constraint programming, in AI, what do you think they should focus on?
Yeah, so I think one of the challenges at the moment is the hype is so big for LLMs and these things that maybe symbolic reasoning feels like completely unattractive, but I'm very confident that 5 years from now, essentially there'll be a big bubble burst when we really hit, we find all the limitations that these current AI systems just can't overcome, and we have to rethink how we do things. Now, plenty of people are going to be trying to do that, so I think that's a really interesting space to be. I don't think you can ignore the powers of machine learning and modern AI techniques. But it is true that even though they're advancing quickly, I think they're always going to suffer from things like hallucination, things like logical fallacies, because they're just not built with these kind of these kind of abilities inside, and it's very hard to see how to incorporate them well. But yeah, it's certainly an area of interest. So I wouldn't say don't be disheartened by the fact that there's this vast world going on, which seems to not care what you're doing, because the customers will care. If you give an optimization solution based on a large language model that just keeps returning unsatisfiable solutions, well, yes, eventually they're going to find that that's not suitable. I think optimization is still a very interesting space. Discrete optimization is never going away. It's really hard. We are getting better at it, and we're learning completely new ways of doing it. And maybe I'm wrong. Maybe quantum computing will start a whole new way of solving some problems. But I'm not convinced. So I think, these understanding the fundamentals of logic, reasoning, these kind of things is a really great starting point for a great career, either in academia or the real world, because these skills are needed, and you can't solve the problems that we care about, problems where there are actual hard constraints, and there's plenty of problems like that. You can't solve them without this reasoning, and no matter how not hot the area is, it's still absolutely required and still has a lot of interesting problems to solve.
Anything we forgot to talk about? Any last words?
Any last words? No, I also joined the CP community because I feel like, okay, it's my home community, but it's also actually a very welcoming and open community. I think, having worked in various other communities, I think we've been very good at, so we talk to each other, even if we're working, on opposing technologies, let's say. It's a community which has a lot of kind of warmth and social cohesion, which makes it a lot of fun to work in.
Right. Thank you very much. This was really interesting.
My pleasure, Gita. Thank you for doing it.
Thanks.